Welcome to Cosmic Whispers, where cosmic mysteries come alive. Your journey beyond the stars begins now. The water creeps higher each year, a millimeter here, a centimeter there. To most, it's imperceptible, but to coastal communities around the world, the rising seas represent an existential threat that grows more urgent with each passing day. By the mid-21st century, sea levels are projected to rise between 20 and 30 centimeters globally, with some regions facing significantly higher local increases due to land subsidence and changing ocean currents. Humanity faces a dilemma that no civilization has confronted at this scale: adapt to the changing coastlines, retreat inland, or innovate entirely new ways to live with water. Among the most ambitious solutions proposed by engineers, architects, and futurists is the creation of permanent floating habitations, entire cities built to rise and fall with the tides, immune to the creeping advance of rising seas. These floating cities aren't merely theoretical concepts sketched on drawing boards. Early prototypes and demonstration projects are already being constructed in sheltered waters around the world. The United Nations Human Settlements Program, UN Habitat, has formally recognized floating cities as a potential adaptation strategy for climate change, lending institutional credibility to what once seemed like science fiction. Every great journey starts with a few brave explorers. Right now, Cosmic Whispers is just beginning, and your support means everything. If you enjoy unraveling the mysteries of the universe, hit subscribe. It's free, and it helps us grow this community together. The physics behind floating cities is deceptively simple, relying on Archimedes' principle, the same natural law that allows massive steel ships to float despite their enormous weight. When an object displaces a volume of water equal to its own weight, it achieves neutral buoyancy. Engineers have refined this principle to create stable, permanent floating structures that can support not just temporary habitation, but the complex infrastructure required for modern urban living. The concept isn't without historical precedent. For centuries, communities in Southeast Asia have built floating villages on lakes and rivers, with examples like Cambodia's Tonle Sap Lake, where entire communities rise and fall with seasonal water levels. In the Netherlands, houseboats have been common in Amsterdam's canals since the 1970s, while in Seattle, Washington, floating home communities have existed for over 100 years. But modern floating cities represent a quantum leap in scale and complexity. Contemporary designs must accommodate thousands of residents, provide stable platforms for buildings several stories tall, generate clean energy, process waste, and withstand extreme weather events. They must create not just shelter, but functioning societies with economies, governance, and social infrastructure. The stakes couldn't be higher. 8 of the world's 10 largest cities are located near coastlines. By 2050, an estimated 800 million people worldwide will be vulnerable to rising seas and coastal flooding. The economic impact of coastal flooding is projected to reach $1 trillion annually by 2050 if adaptation measures aren't implemented. For small island nations like the Maldives, Tuvalu, and Kiribati, floating cities may represent not just adaptation, but survival. With average elevations of less than 2 meters above sea level, these nations face the very real possibility of becoming uninhabitable within generations. As we explore the science, engineering, and social dimensions of floating cities, we confront fundamental questions about humanity's relationship with the ocean and our capacity to adapt to a changing world. The challenges are immense, but human. Ingenuity has overcome seemingly insurmountable obstacles before. Creating a floating city isn't simply a matter of scaling up existing technologies. It requires fundamental innovations in materials, science, hydrodynamics, and structural engineering. The first challenge engineers must overcome is creating a stable platform large enough to support urban infrastructure while remaining resilient to waves, winds, and currents. The most promising approach involves modular construction using reinforced concrete pontoons. While concrete might seem counterintuitive, as a floating material, it offers surprising advantages. When formed into hollow structures, concrete provides excellent buoyancy-to-weight ratios, while offering durability against the corrosive effects of salt water. Modern ultra-high-performance concrete formulations can last over 100 years. In marine environments, compared to just 20 to 30 years for steel structures without extensive maintenance, equally important is the geometry of these floating foundations. Early designs focused on monolithic platforms, but contemporary approaches favor interconnected modular units that can flex and move independently while maintaining overall structural integrity. This biomimetic design, inspired by natural systems like lily pads or mangrove roots, allows the city to better absorb and distribute wave energy during storms. The Oceanics city design, developed in collaboration with the UN Habitat Program, utilizes hexagonal platforms measuring approximately 200 feet across. These platforms can be connected to form neighborhoods and districts, with the hexagonal shape chosen to optimize both structural stability and efficient use of space. The platforms would extend approximately 15 feet below the water's surface, providing sufficient mass to resist excessive motion. Even in moderate seas, scale becomes a critical factor in stability. Larger floating structures naturally dampen wave motions due to their mass and displacement. A comprehensive study by researchers at MIT demonstrated that platforms exceeding 200 meters in diameter can effectively neutralize wave motions of up to 2 meters in height, making them feel as stable as land-based structures during normal conditions. For extreme weather events, additional stabilization systems become necessary. Active ballast systems, similar to those used in large ships, can adjust water levels in different sections of the floating foundation to counteract rolling motions. Underwater skirts, extending below the platforms, create drag that further dampens movement, while shock absorbers at connection points between modules prevent stress fractures during storms. The materials used must balance competing demands for strength, weight, durability, and environmental impact. Beyond concrete, engineers are exploring composite materials reinforced with basalt fibers, which offer tensile strength comparable to carbon fiber but at a fraction of the environmental cost. Recycled plastics transformed into structural components through advanced manufacturing processes offer another promising avenue, potentially addressing two environmental challenges simultaneously. Protection from the ocean environment extends beyond structural considerations. Biofouling, the accumulation of marine organisms on submerged surfaces, presents a persistent challenge. Rather than relying on toxic anti-fouling paints, designers are developing surfaces with microscopic patterns that prevent organisms from attaching while avoiding harm to the surrounding marine ecosystem. Another engineering challenge lies in mooring these massive structures. Traditional anchoring systems would require enormous chains and anchors, creating substantial damage to seafloor ecosystems. Instead, dynamic positioning systems using thrusters and GPS technology could maintain the city's position with minimal environmental impact. Alternatively, tension leg platforms similar to those used in offshore oil operations could provide stability while allowing for controlled movement. The engineering complexity extends below the surface. Underwater habitats connected to the floating city could serve both practical and scientific purposes, housing desalination equipment, research laboratories, and aquaculture operations. These subsurface components would be engineered to withstand hydrostatic pressure while maintaining connections to the surface structures. The success of floating cities hinges not just on keeping residents above water, but on creating self-sufficient systems that provide energy, fresh water, food, and waste management with minimal reliance on mainland resources. These cities must function as living organisms, metabolizing resources and adapting to changing conditions. Energy independence stands as the cornerstone of floating city viability. Traditional power plants would be impractical due to space constraints and fuel transportation challenges. Instead, floating cities would leverage their greatest natural asset, the surrounding water, as both energy source and thermal regulator. Ocean thermal energy conversion, OTEC systems, exploit temperature differences between warm surface waters and cold deep water to generate consistent baseline power. These systems operate continuously, unaffected by weather or seasonal variations that limit other renewable energy sources. Solar energy presents another obvious solution, with photovoltaic arrays deployed both on building surfaces and as dedicated floating solar farms surrounding the city. The water's cooling effect enhances photovoltaic efficiency by approximately 13% compared to land-based installations, while the reflective properties of water increase light capture during morning and evening hours. Wave energy. Converters integrated into the city's perimeter could transform the ocean's kinetic energy into electricity, with the added benefit of dampening wave action against the structures. Freshwater production presents perhaps the most critical infrastructure challenge. Residents would require approximately 50 to 100 gallons per person daily for drinking, sanitation, and irrigation. Conventional desalination typically consumes between 3 and 10 kilowatt-hours of energy per 1,000 gallons produced, making it energy-intensive. However, innovative approaches like forward osmosis and membrane distillation could reduce energy requirements by up to 60%. Atmospheric water generators could supplement these systems by extracting moisture from the humid ocean air. Food production would necessarily transform in these marine environments. Conventional agriculture demands extensive land area, approximately half an acre per person in traditional farming systems. Floating cities would instead rely on stacked hydroponic and aeroponic systems that can produce equivalent yields in 1/10 the space while using 90% less water. These controlled environment agriculture systems would be integrated into residential and commercial buildings rather than segregated into dedicated agricultural zones. Aquaculture would form another critical food production component. Multi-trophic systems combining fish, shellfish, and seaweed cultivation create balanced mini-ecosystems where waste from one species becomes nutrients for another. Research indicates these integrated systems can produce up to 5 times more protein per unit area than land-based agriculture, while sequestering carbon and improving surrounding water quality. Waste management requires closed-loop systems where outputs become inputs for other processes. Advanced anaerobic digestion would transform organic waste into biogas for cooking and supplemental power generation. Black water would undergo membrane bioreactor treatment before being returned to non-potable uses like toilet flushing and irrigation. Solid waste would be separated, with biodegradable components composted and non-biodegradable materials either recycled on-site or compacted for periodic removal to mainland facilities. Transportation infrastructure would fundamentally reimagine urban mobility. Streets would be replaced by a network of canals, pedestrian walkways, and autonomous electric shuttles. The compact nature of floating cities naturally encourages walking and cycling, while water taxis would connect more distant neighborhoods. Bridges and underwater tunnels would link separate platforms, creating redundant circulation systems that maintain connectivity even if individual pathways require maintenance. Building construction would necessarily prioritize lightweight materials and efficient structural systems. Cross-laminated timber, which offers strength comparable to concrete at 1/5 the weight, represents an ideal building material. Its carbon sequestration properties align with sustainability goals, while its modularity facilitates rapid construction and future adaptability. Floating cities aren't merely refugees from rising seas. They represent the frontier of what economists call the blue economy, a sustainable economic model built around ocean resources. While traditional economies often exploit marine environments, the blue economy model seeks to create prosperity while preserving and regenerating ocean health. Unlike conventional cities that rely primarily on imported goods and services, floating cities would necessarily develop economies intimately connected to their watery surroundings. Marine research facilities would become natural economic anchors, attracting scientists studying everything from climate change impacts to pharmaceutical compounds derived from marine organisms. Companies specializing in underwater robotics, autonomous marine vehicles, and ocean monitoring systems would find ideal testing environments surrounding these floating communities. Aquaculture represents perhaps the most immediate economic opportunity. Global seafood demand is projected to increase by 70% by 2050, while wild fisheries are already strained beyond sustainable limits. Floating cities could incorporate commercial-scale aquaculture operations producing high-value species like yellowtail, sea bass, and shellfish. Advanced containment systems would prevent the problems that plague conventional fish farming, such as waste accumulation and disease transmission to wild populations. Seaweed cultivation offers another promising sector. Beyond its culinary applications, seaweed serves as raw material for biodegradable packaging, textiles, pharmaceuticals, and biofuels. It grows at remarkable rates, up to 2 feet per day for some species, while absorbing carbon dioxide and excess nutrients that would otherwise contribute to ocean acidification and dead zones. A single square mile of seaweed farms can sequester more than 20,000 pounds of carbon dioxide annually. Tourism and hospitality would inevitably emerge as economic pillars. The novelty of floating urban environments would attract visitors, while the controlled access inherent to island communities allows for careful management of tourism impacts. Purpose-built education centers would host students from around the world studying marine science, sustainable urban design, and renewable energy systems. Digital industries present a natural fit for these isolated communities. With advances in satellite internet constellations providing high-bandwidth connections virtually anywhere on Earth, knowledge workers could perform their duties remotely while enjoying the unique lifestyle offered by floating communities. Data centers, which generate enormous heat, could use the surrounding ocean for cooling, reducing energy consumption by up to 40% compared to land-based facilities. The maritime industries themselves, shipping, vessel maintenance, and marine technology development would find natural homes in floating cities. Testing facilities for autonomous shipping technologies, drone delivery systems, and marine robotics would benefit from direct ocean access combined with the technical infrastructure and human capital of an innovation-focused community. Perhaps, most intriguingly, floating cities could become centers for developing and deploying ocean cleanup technologies. Systems for plastic removal, oil spill remediation, and algal bloom management could be developed, manufactured, and deployed directly from these communities. The Ocean Cleanup Project has demonstrated that a single passive collection system can remove up to 20,000 pounds of plastic from ocean surface waters annually. Scaled up through deployment from multiple floating cities, such technologies could make meaningful progress against marine pollution. Economic resilience would require diversity and adaptability. Floating cities would likely develop specialized economic niches based on their locations and resources. Those, near major shipping lanes, might focus on maritime services, while those in biodiverse regions might emphasize research and conservation. Cities in tropical regions could leverage year-round growing conditions for agriculture and aquaculture. The financial structures supporting these communities would necessarily evolve beyond conventional models. New insurance frameworks would be required to address the unique risks of floating infrastructure. Blockchain-based systems might manage the shared maintenance of common infrastructure, while innovative financing mechanisms like blue bonds, which fund marine conservation, while providing investment returns, could support initial development costs. Creating floating cities doesn't just present engineering challenges. It raises fundamental questions about governance, sovereignty, and international law. These communities would exist in a legal gray area, neither fully part of existing nations nor completely independent. The legal status of artificial islands and floating structures remains ambiguous under current international frameworks. The 1982 United Nations Convention on the Law of the Sea, UNCLOS, established the concept of exclusive economic zones, EEZs, extending 200 nautical miles from a nation's coastline. Within these zones, countries maintain rights over natural resources, but not complete sovereignty. Floating cities within an EEZ would fall under the regulatory authority of the coastal nation while potentially maintaining some administrative autonomy. Several governance models have emerged as potential frameworks. The first involves floating cities as special economic zones or autonomous regions within existing nations, similar to Hong Kong's relationship with China prior to recent changes. Under this model, the host nation provides defense, foreign representation, and legal foundations, while granting the floating community significant self-governance in local affairs, taxation, and commercial regulation. A more ambitious approach envisions floating cities as seasteads, fully independent political entities recognized under international law. The Seasteading Institute, founded in 2008, has worked to develop legal and political frameworks for such communities. However, achieving international recognition as sovereign entities would require navigating complex diplomatic processes and likely face resistance from established nations concerned about potential tax havens or regulatory arbitrage. The most promising near-term model may be what political scientists call charter cities, new jurisdictions with administrative systems designed specifically for their unique circumstances rather than simply extending existing governmental structures. These cities would operate under charters, establishing their relationship with host nations, clearly delineating responsibilities for defense, criminal justice, taxation, and representation. Day-to-day governance would likely rely on cooperative models rather than traditional hierarchical structures. The physical interdependence inherent in floating cities, where failures in one section could threaten the entire community, naturally encourages collective decision-making and resource management. Digital democracy tools could enable residents to participate directly in governance decisions, while smart contracts might automate certain administrative functions like utility billing and maintenance scheduling. Conflict resolution becomes particularly critical in isolated communities where residents cannot easily relocate. Some proposed floating cities have incorporated arbitration systems inspired by private commercial dispute resolution, with professional mediators and clearly defined processes for addressing everything from noise complaints to contract disputes. Resource management presents another governance challenge. Common spaces and systems like energy grids, water treatment facilities, and structural components require collective maintenance and investment. Economists Eleanor Ostrom's research on common pool resources offers valuable insights, suggesting that user-managed systems with clear boundaries, monitoring capabilities, and graduated sanctions often outperform both private and state-controlled approaches in managing shared resources. Security concerns would necessitate specialized approaches. Traditional police models might be supplemented or replaced by community safety systems, leveraging extensive monitoring technology, dispute resolution processes, and prevention-oriented strategies. The confined nature of floating communities makes certain crimes difficult to conceal, but also creates vulnerabilities to external threats like piracy in less governed waters. Citizenship and residency rights would require careful definition. Would children born on floating cities automatically receive citizenship from their parents' home countries? Would these communities establish their own citizenship criteria? These questions intersect with ongoing international debates about nationality, statelessness, and freedom of movement. Financing governance represents another challenge. Without traditional tax bases like land value or extensive commercial activities, floating cities would need innovative funding mechanisms, user fees for services, community shares in economic enterprises, or resource usage rights might replace or supplement conventional taxation methods. The governance frameworks developed by early floating cities will establish important precedents, potentially shaping how humanity approaches colonization of other frontier environments, from deeper ocean territories to eventual settlements on other worlds. For floating cities to succeed as long-term habitations, they must transcend the paradigm of human settlements merely existing alongside nature. Instead, they must become regenerative systems that actively enhance the marine ecosystems surrounding them. This represents both an ethical imperative and a practical necessity, as healthy oceans are essential for the stability and functioning of these water-bound communities. Traditional coastal development typically degrades marine environments through habitat destruction, pollution, and resource extraction. Floating cities offer an opportunity to reverse this pattern by incorporating biomimetic design principles, solutions inspired by natural processes that have evolved over millions of years. Rather than fighting against ocean forces, these cities would work with them, creating habitats that benefit both human and marine communities. The undersides of floating platforms present ideal opportunities for artificial reef creation. Textured surfaces with varying depths, overhangs and crevices provide attachment points for filter-feeding organisms like mussels, barnacles, and tunicates. These organisms naturally clean surrounding waters. A single mussel can filter up to 15 gallons of seawater daily, removing particulates and excess nutrients. Collectively, a well-designed bioactive hull could process millions of gallons of water daily while creating productive ecosystems. Strategic placement of these artificial structures can enhance natural ocean circulation patterns, bringing nutrient-rich, deep water to the surface through artificial upwelling. This process naturally occurs where ocean currents encounter underwater topography, creating some of Earth's most productive fishing grounds. By mimicking these conditions, floating cities could become centers of marine biodiversity rather than ecological deserts. Light penetration presents both challenges and opportunities. Shadows cast by floating structures can reduce photosynthetic activity in underlying waters. However, this effect can be mitigated through strategic design incorporating light wells, reflective surfaces, and varying platform depths. Some designs propose transparent sections that allow sunlight to reach underwater habitats, supporting seagrass meadows that sequester carbon at rates up to 35 times faster than tropical rainforests, while providing critical habitat for juvenile fish species. Marine permaculture arrays, floating platforms supporting seaweed forests, could surround these cities, creating productive buffers that absorb wave energy while producing valuable biomass. These arrays use deep water pipes to bring nutrient-rich water to the surface, supporting kelp forests that grow up to 2 feet daily while sequestering carbon and creating habitat for hundreds of marine species. Pollution prevention would necessarily become a foundational principle rather than an afterthought. Advanced filtration systems would ensure that no untreated wastewater enters surrounding waters. Microplastic filters integrated into laundry facilities would capture synthetic fibers before they enter the marine environment. Strict protocols would govern the use of chemicals in everything, from cleaning products to construction materials, with preference given to biodegradable alternatives. Noise pollution, often overlooked but devastating to marine mammals that rely on acoustic communication, would be minimized through design choices like rubberized connection points between platforms, electric rather than combustion engines for transportation, and subsurface sound barriers around areas of frequent human activity. Beyond merely preventing harm, floating cities could actively contribute to ocean health through restoration activities. On-site hatcheries could support threatened species reintroduction, while marine science facilities would monitor surrounding ecosystems and develop restoration techniques. Residents might participate in citizen science programs, tracking everything from coral health to marine mammal sightings, creating uniquely informed communities with deep connections to their marine environment. Weather interaction represents another crucial consideration. While engineered to withstand storms, floating cities could also be designed to work with natural weather patterns, potentially incorporating hurricane barriers that double as tidal energy capture systems or rainwater collection systems that prevent flooding while storing fresh water for dry periods. Perhaps most importantly, floating cities would fundamentally reshape human relationships with the ocean, transforming it from a distant environment visited occasionally to an intimate companion in daily life. This proximity naturally fosters environmental stewardship in ways that traditional land-based communities struggle to achieve. The path from theoretical floating cities to functioning maritime communities faces formidable obstacles: technical, financial, legal, and psychological. Yet the convergence of climate necessity, technological capability, and visionary capital has already begun transforming these concepts from speculative fiction to nascent reality. The most advanced initiative currently underway is Oceanic City, developed through collaboration between the architecture firm BIG, Bjarke Ingels Group, the technology company Oceanics, and UN Habitat. In April 2022, the project secured approval from the government of Busan, South Korea, to build a prototype community accommodating 12,000 people in Busan's harbor. Construction is scheduled to begin in 2026, with initial habitation planned for 2028. The estimated cost of $10 billion will be financed through a combination of public funding, private investment, and pre-sales of residential and commercial space. Less ambitious but already operational examples exist worldwide. The floating pavilion in Rotterdam demonstrates modular floating construction techniques while serving as a conference center and climate adaptation showcase. In Amsterdam, the Schoonship community comprises 46 floating homes with shared infrastructure for energy, waste, and water management. Though small in scale, these projects provide valuable real-world testing grounds for the technologies and social systems required for larger communities. Financial models for full-scale floating cities remain challenging. Development costs for conventional land-based urban infrastructure typically range from $50 to $100 million per square kilometer. Floating infrastructure would likely cost 3 to 5 times more initially, though advocates argue that long-term resilience benefits justify the investment. Insurance frameworks represent another hurdle, as conventional underwriting models struggle to assess risks for these unprecedented structures. Psychological barriers may prove as significant as technical obstacles. Humans have evolved as terrestrial creatures with innate preferences for stable ground. Research in environmental psychology suggests that water views increase well-being, but permanent water-based living requires adjustment to constant subtle motion, different acoustic properties, and evolving relationships with weather. Early floating communities would likely attract innovators and early adopters comfortable with these adaptations, while broader acceptance would develop gradually as successful examples demonstrate viability. Regulatory frameworks continue to evolve in response to these emerging communities. The International Maritime Organization has established a working group on floating habitations to develop safety standards and environmental guidelines. Meanwhile, several coastal nations, including France, the Netherlands, and the United Arab Emirates, have created specialized permitting processes for floating structures that don't fit neatly into existing building codes or maritime regulations. The timeline for widespread adoption likely spans decades rather than years. The 2020s will see continued development of prototype communities and refinement of core technologies. By the 2030s, second-generation floating cities, incorporating lessons from early examples, may begin appearing in regions facing immediate climate threats. The 2040s could witness mainstream adoption in coastal megacities looking to accommodate growing populations while adapting to rising seas. Throughout this evolution, floating cities should be understood not as universal solutions, but as one component of humanity's adaptation portfolio. They offer particular value for dense urban centers with limited retreat options and small island nations facing existential threats. They complement rather than replace other adaptation strategies like coastal restoration, upgraded infrastructure, and managed retreat from high-risk areas. What begins as climate adaptation may ultimately open new frontiers for human civilization. Throughout history, necessity has driven innovation that subsequently enables exploration and expansion. Just as early maritime technologies developed for coastal fishing eventually enabled transoceanic voyages, the technologies developed for floating coastal cities could eventually support communities in open ocean environments, harnessing resources and creating habitats far from existing shorelines. As we stand at the threshold of potentially transformative climate impacts, floating cities represent more than technical solutions. They embody humanity's capacity for creative adaptation in the face of planetary change. They remind us that challenges can catalyze innovation, that constraints can inspire creativity, and that our relationship with Earth's oceans continues to evolve as we ourselves transform from land dwellers to potential stewards of both terrestrial and marine environments. In the liquid future that may await us, the boundary between land and sea becomes less a hard edge than a permeable membrane, and our cities may float upon the very waters we once held at bay.